So this is part 3, where we're talking about the dual nature of light again. Last video I talked about how light can be thought of as a wave called electromagnetic radiation, but light can also be thought of as a particle of energy with no mass, but we call that a photon. So part 3 here, let's focus on light being thought of as a particle of energy. Okay, that particle is called a photon. So the particle nature of light, this idea here that light's a particle. The evidence for this comes from an experiment that was first done by Einstein in the late 1800s, and that experiment is sort of, here's what I would do in class with you guys if we were in class to show you this experiment here. So here's a video showing this experiment.
So here I have a black piece of construction paper. We're going to do a little demonstration here to kind of give you a show on photoelectric effect. So this black construction paper has 6 holes in it, and they're covered by 4 different kind of pieces of cellophane: a violet, a blue, a green, a yellow, an orange, and a red. You can kind of see them here as I shine the light across them. So what I'm going to do is I'm going to take out a black construction piece of paper here from the middle that reveals the glow-in-the-dark strip. Okay. First, we're going to let that sit on there so the glow-in-the-dark strip is completely not activated. We're going to take this out, and we're going to set this down on top of white light. And what this is going to do is it's going to have just the purple light come through this filter. Just the blue light, just the green, just the yellow, orange, and red. Okay, but when we turn this off, what we'll find then is that the violet and the blue light are capable of activating the glow-in-the-dark strip, whereas the other 4 are not. So that's showing us that blue light and violet light are of a higher energy and able to activate this particular process in ways that the other 4 lights cannot. If I don't shine them through, and I just put this down on white light, then the blue light and the violet light from that white light are going through, and they're causing that to activate the entire glow-in-the-dark strip. It's only when I take this and do that. Now, we can look a little bit beyond that too, into other types of light, because we also have an ultraviolet light. So we can look at how this black light will cause this to work as well, and what we'll find is the ultraviolet light has even more energy than violet and is able to activate the glow-in-the-dark strip really, really nicely.
So in this demonstration, we had some glow paper, and they had different, they had light. Okay, now what they did with the light is they put some filters on it so that it was different colored light. Red, green, blue, they even used UV at one point. Now, on the glow paper, what happened is that the red, all the way through the green, didn't have the energy needed to actually make this paper glow. So all of those, you didn't see anything with the glow paper. However, the blue light and the violet light and the UV light, all of those were able to make the glow paper glow. So those are higher energies, and the paper was actually able to glow. Now, why does this show that it's a particle and not a wave? It's because if light was a wave, then high intensity red light, like very, very bright red light, would have just as much energy as a low intensity blue or UV light. Like, if I had a lot of red light that was really, really bright, that would have just as much energy as, say, a low intensity, like a very dim blue light or UV light. Those would be equal amounts of energy, essentially, if light was a wave. So the way this works, waves have this property called amplitude. Okay? An amplitude is essentially how high the wave is. So with a wave like in the ocean, you could have a very, very high wave or very, very low wave, and both those waves might have the same wavelength and the same frequency. Okay, now the high wave would have more energy. It would be able to hit things and affect them more. So if light was a wave, if we had red light and it was a wave, it would be able to have a high intensity or a high amplitude, and then it would have a lot more energy than it would if it was a low amplitude. Okay? But this isn't what we see. We do not see the red light ever make the glow paper glow. Right? I could use the brightest, most intense red light in the world, and it would still not affect that glow paper, no matter what. All right? So we know it's not about the amount of energy there, basically amplitude doesn't apply to light, which doesn't quite make sense if we're talking about it. So what we concluded is that light doesn't come as a wave, it basically comes in like a little energy packet. So a red light is an energy packet. It's a little packet of photons, and you get red light that hits it. Or you get like blue light that hits it, which is more energy. It's a little packet of energy, and each color is a different amount of energy. And anything below blue doesn't have enough energy in that energy packet to actually make it glow. So it doesn't matter how many energy packets you kind of throw at it, every energy packet that hits it is going to not have enough energy there. It's just a single packet, and each individual one is not quite enough energy to make it glow, so it doesn't. Doesn't matter how many packets you throw at it, you got to get the energy in there, all in that one little packet or particle of energy here. This is something called the photoelectric effect. It was first observed in the late 1800s, not with glow paper, but with light shining on something, and it actually would eject electrons from the surface of the material. So we would have like really intense red light shine on a metal, and really intense green and blue light shine on the metal, and the more intense, the more energetic color you used was able to actually get electrons, not just glow light. It's easier with glow light to see it, but it would actually have electrons that kind of fly off the material. It's kind of like a solar panel where you get electrons flying off, and you can measure that. You can measure the voltage of it kind of coming off. So, and it didn't matter how bright the light was. Only thing that mattered was the frequency of light. If they shined really, really intense orange light on it, nothing happened. But if they did just a little bit of green, doesn't matter how dim it was, they would at least get something. Okay? Here's another video kind of showing some more.
Now we're going to try something a little different. We saw the pattern that light produced. It's nothing like the sand. But here we've got essentially the same piece of equipment as before, but we're going to turn the brightness of the light down. Here we have the source of light over here. And it's passing through two slits. We've had to cover this up because we don't want any light to get in. The light passes through the two slits, goes over to the other side. Instead of a screen over here, we've actually got a camera because this detects really low levels of light. I'm going to see what we see. Actually, up there on the screen, you can see what the camera's picking up. The first surprise is it's picking up dots, blips. This is light traveling through this, but it's arriving as blips, like the sand, as particles. So that's amazing.
So these little packets or particles of light, we call them photons, okay? Just like we have atoms, we have photons. A photon is just a tiny little particle or bundle of energy. It doesn't have any mass. It doesn't take up any space. It's energy, but it's like a little bundle of energy. And typically, like if we're trying to draw it, since we know it has this idea of like frequency and wavelength here, we kind of draw it as kind of like being a mini wave, like a little packet here that is a wave, but trying to combine the two ideas. Now, the higher the frequency of the color there is going to be higher energy, kind of like we talked about with the waves here. So high frequency means high energy, which means a higher energy photon. So energy is actually directly proportional to frequency. The greater the frequency, the more the energy, because the greater the frequency to make it kind of make the wave, the more energy it takes to make it, so the more energy you're going to get out of it. So the relationship here is E equals HV. E stands for energy, and that's measured in joules. Okay, so the unit for energy is joules. V, again, that's frequency, just like we had in the last equation. That's in hertz, or how many you have per second. Now, the new piece of thing here that is kind of takes some explanation is something called Planck's constant. Right, that's H in this case. Planck's constant is a number that a man named Planck basically calculated. It is 6.626 times 10 to the negative 34 joules times seconds. Okay, the unit there is joules times seconds. So 6.626 times 10 to the negative 34 joules times seconds. And if you are a fan of Stranger Things, Planck's constant actually came up in one of the episodes in season 3, I think. It played a key part to the plot there. All right, so if I want to know the energy of a photon, a particle of light, happens to be red. I want to know its energy because it is a packet of energy. I want to know what that energy is. And it has a frequency of 4.48 times 10 to the power of 14 hertz. So first off, here is my equation. E equals Planck's constant times the frequency. Okay, now in this case, I don't know what the energy is. Energy equals, I don't know. Planck's constant, though, is 6.626 times 10 to the power of negative 34 joules times seconds. Okay, and then the frequency is right here in the problem. So frequency is equal to 4.48 times 10 to the power of 14 hertz. So I'm going to take these numbers and plug them in. So energy, I don't know, so I'm just going to use that as X. Then Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, times the frequency, 4.48 times 10 to the power of 14 per second. Okay, so this one I don't have to do any rearranging. I just have to basically punch this into the calculator. So I'm going to use the sign notation here. 6.626 second e to the power of negative 34 times 4.48 second e to the power of 14. Oops, did I screw up? I use a minus sign of a negative. There we go. All right, so x equals 2. I get 4, 3, so I get 3 significant figures, so I'm going to round that to 2.97 times 10 to the negative 19. The per second and the second cancel each other, so we're left with joules. So a red light photon would have 2.97 times 10 to the power of negative 19 joules of energy. Not a lot. Okay, it's a pretty low energy photon of light. So your turn. What is the frequency of a photon of light that has 8.15 times 10 to the power of negative 20 joules of energy? Okay, so this time we have the energy, and we know Planck's constant, so plug those numbers in, rearrange the equation, and figure out the frequency. Pause the video and give it a try. Okay, so E equals Planck's constant times the frequency. Okay, now Planck's constant, 6.6 times 10 to the 6.626 times 10 to the power of negative 34 joules seconds. I know the energy here, so I'm going to just take this number and plug it straight in. 8.15 times 10 to the power of negative 20 joules is equal to Planck's constant, 6.626 times 10 to the power of negative 34 joule seconds, times frequency. I don't know that, x. Okay, divide both sides by Planck's constant, 6.626 times 10 to the negative 34 joules seconds. Gets rid of that, so the only thing left is x, the thing I don't know. So plug this into the calculator, and I will have my x here. And here's what my calculator says. This got 3 sig figs, 4 sig figs, so I'm going to round it to 3. So this is going to be 1.23 times 10 to the power of 14. And this is, joules cancel, so it's per second now, so that would be hertz frequency. 1.23 times 10 to the power of 14 hertz.